What does a magnitude 5.2 earthquake beneath the ocean actually reveal when it strikes one of the youngest volcanoes on Earth? Is the seafloor simply adjusting to the enormous weight and growth of a submarine mountain, or is magma forcing its way through fractures deep inside the volcano? And when an earthquake swarm begins beneath a volcano that has repeatedly shaken itself apart in the past, how much activity is enough to signal something more serious? On Tuesday, August 11, at 5:48 p.m. Hawaii Standard Time, a magnitude 5.2 earthquake struck beneath Kamaʻehuakanaloa, the active submarine volcano formerly known as Lo'ihi Seamount, approximately 26 miles, or 42 kilometers, east-southeast offshore of Nalehu on Hawaii Island. The earthquake occurred approximately 7 miles, or 11 kilometers, below sea level and was part of an ongoing sequence that began on Sunday, August 9. The Hawaiian Volcano Observatory reported that the earthquakes are associated with unrest at Kamaʻehuakanaloa, while noting that there was no apparent impact on either Mauna Loa or Kilauea. That distinction is important because all three volcanoes belong to the same broader Hawaiian volcanic environment, but they do not behave as if they are simply different openings connected to one enormous shallow magma chamber. The current seismic activity is centered offshore beneath Kamaʻehuakanaloa. For scientists, the location is especially significant because this is not an ordinary earthquake source. It is an active volcano still being constructed beneath the Pacific Ocean. Kamaʻehuakanaloa is a massive submarine volcanic mountain whose summit rises to approximately 975 meters, or 3,189 feet, below sea level. The volcano is estimated to have a volume of roughly 1,700 cubic kilometers, or 407 cubic miles, making it an enormous geological structure despite remaining completely hidden beneath the ocean. Its position makes direct observation extremely difficult. There are currently no working permanent monitoring instruments on the seamount itself, so real-time information about its seismic activity comes primarily from land-based seismometers on Hawaii Island. Scientists can detect and locate earthquakes, but they cannot simply look down from the surface and see whether a fracture has opened, whether magma has moved, or whether the seafloor has physically changed. That limitation gives every significant earthquake an added importance. A magnitude 5.2 earthquake does not automatically mean that magma has reached the surface, and it does not prove that an eruption is underway. Earthquakes can occur when rocks fracture under stress, when fluids move through cracks, when magma intrudes into the volcanic structure, or when pressure changes cause existing faults to slip. In an active volcano, several of those processes can occur at the same time. The earthquake itself measures the sudden release of stored energy, not the amount of magma involved. A relatively small intrusion can potentially produce a noticeable earthquake if it enters rock that is already highly stressed, while magma can sometimes move through existing fractures with surprisingly little seismicity. Kamaʻehuakanaloa has a long history of producing earthquake swarms. Intermittent seismic activity in the vicinity of the submarine volcano has been recorded since at least 1952. That history establishes that earthquakes are a recurring part of the volcano's behavior rather than something completely unexpected. The most energetic known episode occurred between July and August of 1996, when more than 4,000 earthquakes were recorded. Nearly 300 of those events were larger than magnitude 3.0, while 95 earthquakes fell within the magnitude 4.0 to 4.9 range. The sequence became one of the most important episodes ever documented at the submarine volcano because the intense seismicity was accompanied by major changes at its summit. The 1996 crisis demonstrated that an earthquake swarm beneath Kamaʻehuakanaloa can be connected with physical changes to the volcano itself. During that period, a new collapse pit formed in the southern part of the summit caldera. The feature became known as Pele's Pit and remains one of the clearest examples of how the submarine volcano can restructure itself during major unrest. The crater is approximately 600 meters, or 1,970 feet, across, and its bottom lies roughly 300 meters, or 985 feet, below the previous summit surface. The event did not produce a directly observed eruption, but it showed that powerful seismic activity can accompany significant collapse and deformation at the summit of this hidden volcano. That history is one reason scientists will pay close attention to the August earthquake sequence without automatically assuming that it will repeat the events of 1996. The current magnitude 5.2 earthquake is significant, but the 1996 episode involved thousands of earthquakes over an extended period and produced profound structural changes. A single magnitude 5.2 event cannot be compared directly with an entire swarm of more than 4,000 earthquakes. What matters is whether the present sequence continues to develop. If additional earthquakes accumulate, scientists will be able to compare the new activity with previous episodes and determine whether its behavior resembles ordinary unrest or something more unusual. There is another important comparison from May 11, 2020, when approximately 100 earthquakes occurred near Kamaʻehuakanaloa. 18 of those events were between magnitude 3.0 and 3.9. That swarm eventually passed without becoming an observed eruption. The episode demonstrates why earthquake swarms beneath Kamaʻehuakanaloa should not automatically be interpreted as countdowns to an eruption. The volcano can become noticeably restless and generate clusters of earthquakes without producing lava at the seafloor. Its seismic behavior is naturally episodic, and periods of increased activity can occur without progressing into a major eruptive event. The present activity therefore fits into a broader pattern that has been unfolding for decades. Kamaʻehuakanaloa is a restless submarine volcano, and earthquakes are one of the clearest ways that scientists can observe its internal activity from land. The current magnitude 5.2 event is notable because it is considerably stronger than the small earthquakes that normally make up background seismicity. Yet magnitude alone cannot determine what caused it. Scientists need to examine its precise location, depth, waveform characteristics, and relationship to surrounding earthquakes before drawing conclusions about whether magma movement played a role. The volcano itself provides clues to its complex internal structure. The summit is marked by a caldera-like depression, approximately 2.8 kilometers, or 1.7 miles, wide and 3.7 kilometers, or 2.3 miles, long. 3 collapse pits or craters occupy the southern part of this depression. Pele's Pit is the youngest major crater and formed during the 1996 earthquake crisis. These features show that the summit has repeatedly responded to changes within the volcanic system. A submarine volcano does not need to produce a spectacular eruption to change its shape. Pressure changes, magma movement, withdrawal of material, or structural failure can all contribute to collapse and deformation. Kamaʻehuakanaloa also has an extensive rift zone that stretches approximately 31 kilometers, or 19 miles, northwest and southeast from the summit caldera. Rift zones are important because they allow magma and volcanic stress to move away from a central summit region. Hawaiian volcanoes are not simply vertical tubes with magma rising directly upward. Their internal plumbing systems can extend laterally, with magma exploiting fractures and zones of weakness in the surrounding rock. Earthquakes occurring along or near these pathways can therefore provide information about where the volcanic structure is responding to changes in pressure. If the current earthquake sequence remains localized, that could suggest a relatively confined zone of stress or adjustment. If seismicity spreads along the rift system, scientists could examine whether the volcano is responding over a wider region. If earthquakes begin migrating toward shallower levels near the summit, that could provide another signal worth watching. None of these patterns would automatically prove that an eruption is coming, but each could change the scientific interpretation of the unrest. Volcanologists generally look for multiple independent signals before concluding that a volcano is moving toward eruption. One of the biggest challenges at Kamaʻehuakanaloa is that those additional signals are much harder to observe than they would be at a volcano on land. On Kilauea, for example, scientists can combine seismic data with ground deformation measurements, gas observations, thermal imagery, visual observations, and direct field surveys. Kamaʻehuakanaloa sits under the Pacific Ocean. Its summit is roughly a kilometer below sea level, and there are no working monitoring instruments directly on the seamount. The primary real-time observations, therefore, come from land-based seismometers, which listen to the seismic waves traveling from the submarine Volcano toward Hawaii Island. That monitoring network is still extremely valuable. Modern seismometers can detect earthquakes far too small for people to feel. By comparing the arrival times of seismic waves at multiple stations, scientists can estimate the earthquake's location and depth. A sequence of hundreds or thousands of events can reveal patterns that would otherwise remain invisible. Earthquakes can form clusters, migrate, deepen, or become shallower, and these changes can help researchers understand how stress is moving through a volcanic system. Even without instruments sitting directly on the summit, the seismic record can provide a powerful indirect view into Kamaʻehuakanaloa. The problem is that indirect observation has limits. Scientists cannot directly measure every tiny change occurring at the seafloor. They cannot continuously inspect the walls of the summit caldera from land, and they cannot easily determine whether a newly fractured zone has produced a small submarine eruption unless other evidence becomes available. Deep-sea surveys and remotely operated vehicles can provide extraordinary information when they are deployed, but those observations are not equivalent to having a permanent monitoring network on the volcano. This makes the seismic sequence following the August 11 earthquake especially important because it may be the clearest real-time indicator of how the system is behaving. Kamaʻehuakanaloa has never had an eruption directly observed by scientists. That may sound surprising for a volcano known to be active, but its location makes observation exceptionally difficult. Research indicates that eruptions at the seamount can be both explosive and effusive. The volcano is currently considered to lie between the pre-shield and shield stages of Hawaiian volcanic development. It is therefore still in an early phase of construction compared with the enormous mature shield volcanoes that dominate Hawaii Island. That early stage is one reason Kamaʻehuakanaloa is scientifically fascinating. The volcano represents a younger phase of the same broad geological process that has built the Hawaiian Islands. It began growing beneath the ocean and has continued accumulating volcanic material over geological time. Lava flows, magma intrusions, structural collapse, and repeated deformation have gradually transformed the seafloor into a massive volcanic mountain. Its summit is still hidden nearly 1 kilometer below sea level, but the volcano is already enormous. Its estimated volume of approximately 1,700 cubic kilometers, or 407 cubic miles, demonstrates just how much material has accumulated below the ocean. The Pacific hides most of that mountain from human view. If the summit were above sea level, its scale would be obvious from surrounding communities. Instead, the ocean conceals the volcano and leaves seismometers on land to detect many of the changes occurring inside it. The long-term future of Kamaʻehuakanaloa is equally remarkable. Scientists do not know when the volcano will eventually reach sea level. A rough growth rate of about 5 meters, or 16.4 feet, per 1,000 years has been used to illustrate how slowly the volcano might rise under certain assumptions. At that rate, reaching the ocean's surface from its present elevation could take as much as 200,000 years. But that calculation should not be treated as a geological timetable because volcanic growth is highly uneven. Long periods of quiet can be interrupted by much more productive eruptive periods, dramatically changing the rate at which the volcano gains height. The future could therefore involve long intervals of relatively modest activity, followed by periods when enormous amounts of lava are added to the volcano. A single earthquake swarm does not determine the future growth rate. Instead, the volcano advances through countless individual geological events. Every intrusion, lava flow, collapse, and structural adjustment contributes to its evolution. The magnitude 5.2 earthquake is only one event within that much larger process, but it provides another opportunity to study how the volcano responds to stress. The Hawaiian volcanic environment also involves enormous mechanical forces unrelated to a single magma intrusion. The Hawaiian Islands are built from gigantic volcanic edifices that place immense weight on the underlying crust. That weight bends and stresses the lithosphere. Some earthquakes in Hawaii are related to the movement and storage of magma, while others are associated with faults and deeper structural adjustments caused by the weight of the volcanic islands. Around Kamaʻehuakanaloa, volcanic construction and crustal stress interact in a particularly complicated setting. This is why scientists do not automatically assign every earthquake beneath a Hawaiian volcano to magma. The rock can fracture because of several different processes. A magma intrusion can change pressure. Fluids can move through existing cracks. Faults can slip when stress reaches a critical point. The weight of the volcanic edifice can alter the surrounding crust. These mechanisms can overlap, making earthquake interpretation a matter of studying patterns rather than relying on one event. The depth of the August 11 earthquake is another important detail. The event occurred approximately 7 miles or 11 kilometers below sea level, while the summit of Kamaʻehuakanaloa is roughly 0.6 of a mile or 1 kilometer below sea level. That places the earthquake several kilometers beneath the summit region, rather than immediately at the volcanic peak. Its location, therefore, does not by itself demonstrate that magma was moving toward the seafloor. More information about the surrounding earthquakes will be needed to determine whether the activity is concentrated at depth or migrating through the volcanic structure. For residents of Hawaii Island, the earthquake itself is also more important than the dramatic imagery that can surround an offshore volcanic event. A magnitude 5.2 earthquake can produce noticeable shaking, but the effects depend heavily on distance, depth, local ground conditions, and the characteristics of the rupture. The earthquake occurred approximately 26 miles, or 42 kilometers, east-southeast offshore from Naʻalahu, reducing the intensity compared with an earthquake of similar magnitude directly beneath a populated area. Another obvious concern is whether an earthquake beneath an underwater volcano can generate a tsunami. An earthquake does not automatically produce one. Significant tsunami generation generally requires substantial vertical displacement of the seafloor that transfers energy into the ocean. Many earthquakes produce little or no tsunami because their rupture geometry does not significantly lift or lower the seafloor. The current magnitude 5.2 earthquake has not been identified as producing a destructive tsunami, and the available information does not indicate that the event created a major ocean-wide tsunami threat. The more significant scientific concern is therefore what is happening inside the volcanic system. The earthquake sequence began on August 9, and the magnitude 5.2 event occurred 2 days later. Scientists will be interested in whether the number of earthquakes increases, whether their magnitudes change, and whether their locations migrate. A swarm that rapidly fades can represent a short-lived episode of unrest. A swarm that continues for days or weeks can provide a much richer picture of the volcano's internal behavior. For now, the evidence does not support claims that a major eruption is underway. It does not show that the volcano is about to breach the ocean surface. It does not indicate that Hawaii Island is facing an immediate volcanic crisis from Kamaʻehuakanaloa. What it does show is a young and active submarine volcano experiencing renewed seismic unrest at a location where scientists have documented powerful earthquake sequences before. And that is enough to make this earthquake worth watching. Kamaʻehuakanaloa remains almost a kilometer below the surface of the Pacific, but its seismic signals have reached the instruments on Hawaii Island. Those signals are now being added to a record that stretches back more than 7 decades. Every earthquake adds another piece of information about the hidden architecture of the volcano and the forces shaping it. The youngest known Hawaiian volcano is still growing, still fracturing, and still changing. Whether the current swarm fades quietly or develops into something larger will depend on what the volcano does next. For the moment, the most important fact is simple. On August 11, a magnitude 5.2 earthquake shook the interior of Kamaʻehuakanaloa, providing another reminder that one of Earth's most remarkable volcanic systems is still alive beneath the Pacific.